So, we record the lectures for YouTube. That's okay. You can put it maybe outside pockets so that antenna is. Yeah, perfect. That'll be fine. Is that comfortable? Okay, thanks.
Really, okay. One more than the curious.
You always do ways for technical side. So I think this is a new grid of film.
Oh. Yeah, I just. Okay. Very low.
Wait like 1 hour.
Oh, okay, yeah. See, here's the thing, you don't want a lot of, especially.
You are chairing?
Yeah. The number of that. The facts.
This is not many good stuff. Blind and China on ANA business is more like $100.
Yeah, I got. Yeah, mine also trying just like a trip to India.
I haven't.
But to think if you.
That's sweet.
What is this?
You should. Yeah, you should get like. So I mean, like, you like
So do I need to do anything here?
Is there green
Yeah.
light? Okay. Yeah, that's okay. So today we'll begin with our first lecture from Shan from the MPI and Berg and Cornell. And she'll be giving 3 lectures. Her first lecture is on optical spectroscopy in 2D.
Okay, thank you. Can you hear me well in the back? Good. So I realized that most of you are theorists. So, and I ask myself, and I also ask the organizers, what an experimentalist can share with you. So I was told I should talk a little bit about techniques. So this is what I'm going to do today. And tomorrow I'm going to give you an overview of recent experiment developments on semiconductor marine materials. And on Friday morning, I'm going to talk about electron and whole double layer systems. So let me start with optical spectroscopy of 2D materials. So, for those of us who are interested in fundamental properties of 2D materials, this is usually what we do. So we start with some bulk crystals, layered structures bounded by weak van der Waals force. We exfoliate them. You heard of a Scotch tape, and basically that's still the technology. And then we can stack them pretty much of arbitrary composition very precise alignment in terms of crystal position and orientation. And this can be done because of the van der Waals nature of those materials. So you can isolate a single unit of stable layer, and they don't care about the lattice mismatch too much. So you can put the different materials together. So once we have this, we can do lithography. You probably have seen a little bit from Philip Kim's talk. So we shape the sample into some structure we like. If you want to do transport measurement, magnetotransport measurements, you shape it into whole bar. So you add those electrodes, put on gates. And the way to think about this, it's just some kind of parallel plate capacitors. And now you can come in to do your measurements. So in terms of experimental probes, this scale bar you can see here is about 10 microns. And this pretty much, what we can achieve with those materials. Electrical transport measurements are pretty straightforward, because of the early development of micro structures, But you need to figure out how to put the contacts on. So for graphene, it's relatively easy, but for semiconductors, usually that's challenging. The reason is because you have a band gap. If you want to put a metal on it to avoid the Schottky barrier, you need to find the appropriate material to get good ohmic contacts. And this is something experimentalists work very hard on, especially if in your material you have different types of semiconductors. One is electron doped, the one is hole doped, as what I'm going to talk about on Friday. This is extremely difficult, to find different contact materials to achieve both electron and hole contacts. And thermodynamic measurements, I'm talking about chemical potential, magnetization, polarization, entropy, specific heat. Those measurements are extremely challenging. And the reason is because, we are dealing with one atomic layer or few atomic layer materials, and you have micron square, roughly the size. And you just don't have too much material to work with if you want to get thermodynamic properties. And often they are embedded in a bunch of other structures, and they can dominate your signal. So those are the difficulties. And optics is kind of a convenient because it can penetrate through. It's relatively non-invasive because you don't need electrodes, things like that. So, I will talk about optical measurements, and using optical measurements maybe infer some of the electrical properties and thermodynamic properties. So those 2D materials are pretty good test bed for theoretical models because we have a lot of control knobs. So just imagine you have parallel plate capacitor, so you can put a gates on your voltage on your gates. So you can control doping density, you can control displacement field perpendicular to your sample. You can strain a little bit, and you can also change the environment, for example, change the dielectric screening of electron-electron interaction. And we can also use light to change the properties. So a lot of controllable knobs, and you can get, for example, a phase diagram of complicated many-body phases in a single device just by changing, for example, some of the voltages. Okay, so today, as I said, I'm going to focus on optics. And optics actually played a very important role in the early days of 2D research. So this is a paper from 2005, so you see it, then you know what you have, right? So this is pretty much what this is. So Novoselov and Gaim, they put exfoliated thin films on silicon substrate, but not just the silicon substrate with very thin oxide layer as what we have. It has a little bit thicker, 200 to 300 nanometer oxide layer. And then you can see a very clear contrast of thin film on substrate. So this is a substrate, and it has kind of an interesting color. So silicon has a band gap smaller than visible and light energy. It should look black, but this has color. And the reason is because you have this thin oxide layer, and this is due to the interference effect. It's like oil on water. You see this kind of color. And this helps to see those layers, okay? Okay, so what can optics do? So if you do linear optics, you can get optical response, and that will give you information about electronic properties. If you look at a pretty much visible UV, you can look at the infrared, you will see vibration modes, and then you can look at the rotation at a lower energy. And at even lower energy, somewhere you will see collective excitations. So that just to look at the sort of power or intensity change of light, and you get absorption. And light is also wave, electromagnetic wave. You have polarization. So if you keep control and measure the polarization, and this is called, we have this name here. So if you keep track of polarization, you can probe different symmetry breaking states, whether it's rotational symmetry breaking, time reversal symmetry breaking. So that's polarization. And you can also look at the nonlinear optics. I think Peter probably mentioned this a little bit earlier, right? In this summer school, if you have a non-central symmetrical material, you have nonlinear stability. If you look at, for example, second harmonic generation, you will be able to tell the crystallographic orientation where the armchair or zigzag crystal axes are. And that's very important when we work on heterostructures to form moraines, because you need to know where are the crystal axes, and this can help you to do that. For lattice vibration, people often do Raman spectroscopy, and Raman can also tell you a little bit about collective excitations. And then, experimentalists sometimes can also be very creative. We come up with ways to do different measurements, using optics to read out transport properties, read out the thermodynamic properties. And this is something I also plan to talk a little bit about today, so that you will not be totally bored. So in the next 30 or so minutes, I'll be talking about something, basic undergraduate optics, okay? So the key is how to get optical response from the measurement. And I told you, we work with a relatively small sample, so we need to focus down light to some small spots. And this is a typical measurement scheme we use. And the setup has a name, it's a confocal optical microscope. And this allows us to do local measurements on the order of wavelength, that's the size. And you can scan around, so to get a profile. So the setup is pretty straightforward, So you have some kind of a light, it could be light, it could be just a lamp. It goes through a pinhole. So now you make it point source, right? And then it hits a beam splitter, and the part of beam is reflected, and you use a microscope objective, for those of you who have seen us from biology, something really big. And then this, you can focus it down to the sample you want to study. And then you look at the reflection back or emission back from your sample, and it's collected by the same objective, goes through the beam splitter, and then collected by your detector. And the detector can disperse to get a spectrum, or you put a filter to look at the second harmonic, or just look at the reflection. But there's this pinhole. So this is why it's called a confocal. So if you have light emitted or reflected from other spots other than your focal plane, it will be blocked by the second pinhole. Okay. And so this is a reflection measurement, and you can also do transmission. But for devices on silicon substrates, usually reflection is the mode. Okay. So the measurement is simple. How do we get response from this measurement? So this is what I'm going to talk about in the next 20 or so minutes. So first, let's just model this. So we are interested in optical response of thin film. So here's our substrate and a thin film on top of it. And for simplicity, I make it semi-infinite, this substrate. And this is okay, although your substrate could be finite, but we have a pinhole. That means all the reflection from the back surface will not reach your detector. So effectively, this is semi-infinite substrate, okay? And in this picture, although the light is focused down, but it's still a pretty good approximation to just use plane wave. So this pretty much just a thin film on a semi-infinite substrate, and we have light coming, let's say normal incidence, and a part is reflected, and with this reflection coefficient R, and those are for fields, right? The ratio of the fields. And then we have part is transmitted. Right? And then I can call this axis to be x0, and then you define your coordinate. And let's assume the film thickness is D. And we're interested, let's just also assume we know what kind of a substrate we have with refractive index NS. So the material, right? So in 3D, you can describe the property using a few different quantities, but they are pretty much just the same, depending whether you are a transport guy, you are optics person, right? So transport people like conductivity. And that's sigma. Sometimes you say stability, and that's chi. And you also hear people talk about dielectric function. So that's epsilon and epsilon naught, where this is the vacuum permittivity. Or optics often talk about reflective index. And all those are complex functions of frequency or wavelength, right? And they are connected. So for example, conductivity is just the minus I chi epsilon naught omega, where omega is the angular frequency of light, right? So chi, and you can convert this, it's the same as I sigma epsilon naught omega. The dielectric function is just 1 plus chi, and I'm using SI unit. And n is just the square root of epsilon. So pretty much just the same thing, right? So we want to get the frequency dependence of one of those quantities from this measurement, okay? And then for 2D, often we use sheet conductivity or sheet susceptibility. And this is sigma multiplied by the thickness of the sample, or sheet susceptibility. So that's pretty much the quantity we want to get. And how to do this, I think that Peter already talked about, you're doing Fresnel equations or transfer matrix operation, right? So I'm not going to bore you with how to get this. So I just show you the result you probably have already seen in his lecture. Okay, so for 3D slab, this is what you can get from transfer matrix. Or you just do Fresnel equations, you will get this. So reflection coefficient is the electric field of the reflected light divided by the incident field. And the transmission, again, is the ratio of the field transmitted versus divided by incident. So looks like a complicated, but we will not be bothering about this. So what's here, NS is the substrate index. Phi is the phase shift, one pass through the thin film. So it's 2 pi reflector index thickness divided by the wavelength. And the phi 0 is the phase shift if it's in vacuum. Okay, so this is accurate, no approximation here. So the assumption here is that the medium is isotropic, homogeneous, and it's a plane wave. So this is the only assumption. And in experiments, except terahertz time domain spectroscopy, you heard from Peter, there you can measure electric field as function of time directly, but for visible UV or other wavelengths, usually you cannot measure electrical field directly. What you measure is power, which is proportional to module square of those fields. So in the experiment, what we get is reflectance, which is modulus this guy's square, or transmittance. Sorry, this is R, and the T. And because we have substrate, so it's not just the modulus T square, we have real part of the substrate index. And then, of course, we have absorption in the film, and then absorption. You can derive it, but it should obey energy conservation. So this is absorption. Okay, so this is just a kind of generic 3D slab, and the question is, if we work with a very thin 2D materials, can we simplify this? And you see here, what's important is this phase shift. So if phase shift is small, so in the case when phi maybe I'll do on the other side. So now if phi is much, much smaller than 1, we can just expand the sign So cosine phi will be 1. We just keep it the leading order. Sine phi will be 1. And ei phi 0 will be 1 minus I phi 0, right? Because if phi is small, then phi naught is also small. So if you do all those expansion, we get a simplified version. So R is going to be 1 minus NS minus Z0 sigma sheet conductivity divided by 1 plus NS plus Z0 sigma S. And where this Z0 sigma sheet conductivity is minus I n square minus 1 I naught. And this Z0 is in free space impedance. So it's epsilon naught C. And in terms of value, it's 377 ohms. Okay. And we can write down the same thing for T. It's 2, 1 plus NS plus Z0 sigma S. Okay. And this is kind of interesting. So, in this model, we just ignore the propagation effect, right? We assume phi is small. And you can see that if you look at the difference, for example, if I look at the delta R, which is this R minus R0, this is in the case of no thin film. So this is like change of refraction coefficient. If you do this simple manipulation, you can convince yourself that delta R is the same as delta T. So the change in refraction coefficient or transmission coefficient is the same. And this makes sense because we ignore the propagation effect. And we can do more approximations. So if now Z0 and the sheet conductivity also small, then we can linearize this, right? So the next thing we do will be linearize the 2D. So in that case, Z0 sigma S, the modulus we assume is much smaller than 1. So if we look at what this is, it says I n squared minus 1, right? So if we just ignore 1, what's left would be n squared phi naught. So basically, this is just pretty much just n phi. So if this is much smaller than 1, we can linearize this equation. So R is going to be R naught when we have the refraction coefficient without the thin film. 1 minus 2 times 1 minus n s squared Z0 sigma S. And the T is going to be T naught 1 minus. So now this looks kind of a simple. And then for experiment, if we come back to the setup, so what I can do, I can move my sample, so say my sample at one location and I move to a different part of a substrate with no sample. So I can look at, for example, the change in transmission or change in refraction. So this is something easy to do. So in experiments, I'm going to look at differential reflectance or differential transmittance. And sometimes this is also called refraction contrast or transmission contrast. So by definition, this is delta R over R0. So it's R minus R0. And this is just the real part of some factor that depends on the substrate refractive index, Z0 sigma S. And then delta T over T0. Negative. Okay. And then, of course, we also have A. Okay, so now just by looking at those three lines, looks like a mission accomplished. But then the question is, how can we get the complex? Yeah, go ahead. Nothing is stupid. Uh-huh.
I just I know because the sensor same index but this does not reflect.
Okay, so you are saying, now if I make Z0 sigma S to, if you look up there, so the real part is 0, right? Because this is I n square minus 1 phi naught, right? So it's purely imaginary. So real part of that is 0. You agree with me?
Right, but the formula for R naught for R.
Yeah. No. So nothing will change if you just replace the index of your sample and a substrate to be the same.
Yeah,
Just,
I was just thinking that it's a small R and small.
okay. So did I miss anything? So this would be yeah, but your it should go to 0. So you actually raised a very good question, when are those approximations applicable? And now let's take a look at that. So if you go back to the original result for 3D slab, it should be okay, right? But when we get to the linearized, the 2D model, we've already made a series of assumptions, right? So those approximations. Let me just draw. So the quantity we look at is this modulus of phi, right? So when phi is very, so we compare to 1, or we compare to 1 divided by n, right? So for any phi, this 3D slab model is okay. It's rigorous as long as it's homogeneous, isotropic, right? But for this 2D model, we want phi to be smaller than 1, right? So this is for 2D model, the one up there, right? But now if we want to use the linearized 2D model, this needs to be much smaller than 1 over n. right? So those are the approximations. So the question is, how do we determine this complex Z0 and sigma sheet conductivity for the measurements? And you may just say, okay, I'm interested in this complex quantity. I have a real part and imaginary part. I need to do 2 measurements. Once I have 2, I should be able to solve to get real part and imaginary part, right? This is not quite true because, if you just look at the simple case, if the substrate index is real, then both refraction and transmission give you very similar information. So you get only the real part of this. And often this is enough, but in order to get the full complex information of the sheet conductivity, you may do, for example, 2 measurements, one with a transparent substrate when this NS is real, and then move to a different substrate when NS is complex, and combining those 2 measurements, you can get, information of a real part and imaginary part.
Could you maybe remind us what are the typical values here?
Okay, yeah. So for substrate, well, N of course is frequency dependent, right? So for transparent substrate, like a silicon oxide, for a very large range, N is about 1.5. For the materials, we are talking about, it could be, 5 or something, 3, 5,
So 1/n isn't that small.
1/n is not that small. Okay, so that's kind of the strategy, people can use.
Maybe you can comment like how easy is it to, let's say if I do this substrate experiment, like
It's not that easy for those 2D materials because you may string your sample a little bit, you may accidentally dope your sample a little bit. So it's not that easy.
Yes, is there also like is frequency dependence like the frequency dependence of some complex NS enough to get like strong signal?
Yes, exactly. So this is the first picture I showed you. People use 200 to 300 nanometer silicon oxide, silicon as substrate. So you can engineer your substrate such that you can enhance the property. Yeah, that's an excellent idea. So changing substrate is not that straightforward. And one other thing you can do, remember, all those properties need to obey chronic. Exactly. So they have to yeah, so Kramer's chronic relation is another way to get around. So if you model your material, with some function and the built-in Kramer's chronic requirement for real part, imaginary part, and then fit your experimental result using this, and then you iterate, modify your input for the conductivity, then, after many times, you may get, what this is. But the complication here is that, remember, for Kramer's chronic relation, it is for infinite spectrum. So you need to have, low to very high spectrum. And for optical measurements with very limited range of frequencies or energy, the Kramer's chronic is not very good. Okay, so those are the complications. Okay, so now let's take a look at some real material and see whether any of those approximations are good. Okay, so I'm just going to show you some simulation from this paper. So on the left, what I'm showing actually is the realistic optical properties of 3 different types of materials. So the first is a single layer semiconductor tungsten selenide, tungsten sulfide. And sorry, it's a little bit small. So the first column is the real part of dielectric function. And the second column is the imaginary part. And then column C is the computed phase shift, one pass through this one layer. And the range is, in the visible somewhere. And you see the middle column is something you usually see when you look at the optical spectrum, you see some absorption peaks, looks like, right? So those peaks are due to excitons in this material, electron-hole interaction. So some, band edge is very close to it. And you see multiple peaks, there are multiple exciton resonances. For the imaginary part, you see some kind of a funnel-like line shape, and that's due to interference of this discrete levels with continuum. So the column C is important. If you look at the values, it says a few percent. So phi is small. So in this case, the highest is about 0.05, right? So according to this, for monolayer moly sulfide, this 2D simplification is okay, right? And this is what you see on the right. The red is for the simplified 2D model, and the green is for the complete 3D model. And you don't see any difference. So in this case, it's okay to use this 2D model. Right? So the next example is for monolayer graphene. This graphene, in this case, is doped. You raise the Fermi level to about 0.3 electron volts. So the lower part is just due to free carrier intraband transition. So this is just a Jude model. And then above 0.3, you have band-to-band transition. And this is much weaker. It's multiplied by 50 times. So this is the real part of the dielectric function, imaginary part. And this is something, we assume we know, you put it in. And this is a computed phi. And you can see, phi is also a few percent, and that's also small. So you expect the 2D model to be okay. This is okay. And then the last example is a very thin film, 10 nanometer gold. You use the typical Jude, density, scattering rate. And phi now get up to about 0.5. But it's still smaller than 1, right? And you can see that, the 2D model is still pretty good. Okay, yeah.
Is that the same price that you had over there?
Yeah, yeah.
But does that depend on D? Thickness of.
No, phi depends on D, yeah. So for this materials, we know, like for monolayer tungsten, yeah. So the first example thickness is about 0.68 nanometer. The second is half of it. And the third one is 10 nanometer. Yeah. So, and the lesson we learned from this, for 2D materials, if they are not too thick, 5 layer, 10 layer, they're okay. You can use the 2D model. Okay. So what's kind of interesting is that material can be strongly absorbing, but they can still be considered, this 2D. Okay. So the next example is to see whether we can use this linearized 2D. Again, for the same 3 examples, now I'm showing here is not the dielectric function, but the sheet conductivity. but I multiply by Z0, so it makes it dimensionless. So the real part, real part of the sheet conductivity, imaginary part of a sheet conductivity. And now you can see this, oh, this is just, that's what you see in absorption spectrum, right? The middle column. For monolayer of tungsten sulfide, you can see that the single sheet can absorb 20%. So this is significant. And if you look at this parameter Z0 sigma, it's small for the whole background, but at the peaks, at the exciton resonances, they are not that small. And then that you can see from the comparison. So the 2D model is just the red line, and this linearized 2D is the purple line. So even for single layer, this linearized model often, does not give you a very accurate result. And this is what you can see here. And of course, for 10 nanometer gold, totally out. You cannot do it. It's completely different. Okay, so yeah.
What do we gain from using the link? If you just take the equation,
Yeah.
there, you can invert them and find the sigma.
Yeah.
Exactly.
Yeah, sure, you can do that. So it's just for convenience, because here, it's linearly proportional to, this is what you measure, and this is something you get, linearly proportional to immediately. You have this information. Yeah, so you're right. To get, accurate results, use the complete 2D model.
And is it more complicated in terms of the data analysis, or just a few more steps?
So if you look at lots of those experimental papers, they even don't do this. They just show this. Yeah. Yeah.
So in that case, why would delta R over R, which is the experimental value was not?
Oh.
That's what you don't measure.
Yeah, we measure it, but the goal is to get sheet conductivity, for example.
Right, so I was saying, but
No, so this model just tells you, this simulation just tells you, the model is applicable or not applicable.
so this one is using the same conductivity.
No, this is assume you know conductivity, but in experiments, when you just measure something, you don't know which model is applicable, right? So this gives an idea. Oh yeah, this is opposite. It's a transparent substrate, like this 1.5 I was talking about.
Yeah, I just had a very simple.
Yeah.
Details question. So in the 3D model, you have in the numerator, you have for the reflection coefficient NS minus N squared.
Yeah.
Bottom and S plus N squared.
Bottom.
No.
This is.
Yeah, that one. For R, little r.
Yeah.
The second term in the numerator and the denominator. No, second term.
Yeah, this. Why this is not square? This is.
No. So it's plus. That one's plus, and the numerator is minus.
Oh.
But then but both.
Okay.
Okay,
You
call them Z0 sigma S. Is that am I misunderstand something?
Or I made a typo.
Oh, okay.
I don't know.
They're both the same quantity. Z0 sigma S.
Z must.
You call them.
Wait. I don't quite understand what you're asking. So Z0 sigma S is N squared minus 1 minus I phi naught.
Right.
Yeah.
But in the numerator, plus.
It's a typo or, oh, so let me not spend time here checking the size. So
It's the same quantity.
yeah. So this is a reference. So let's check this. Okay. Yeah.
But in all these experiments, you know, there's a film here and I'm sending light like this.
Yeah.
Right? So always we're measuring like the CC component of the response function.
The in-plane response in this case, because electrical field is in plane. Okay, so now let's get back to this experimental question. If I measure something like this, do I know whether I can use the 2D model or linearized 2D model, right? So, if this ratio is small, much smaller than 1, then it is safe to use the linearized 2D model. But otherwise, one needs to be very careful. So that's kind of the general idea. So again, as I said, 2D sheet can be strongly absorptive, but at the same time, optically thin. Right. So the next question is, what is the maximum sheet absorption we can get? So if we just look at, for example, this simple relation, we can also look at there. So we can. So the question is, what is the maximum 2D absorption we can get? So a maximum. You can get the expression for A, which is 1 minus R minus T, right? So here's R and here's our T, modulus square, right? With the right index. And then you can use this sigma sheet conductivity as variable and find the 0 for the first derivative. And this happens when if Z0 sigma S is NS plus 1. And in that case, a maximum is 1 divided 1 plus 1. So the simple algebra, I'm not going to go through. So what this says, if the sheet conductivity multiplied by the vacuum, free space impedance is 1 plus the index of substrate, you get maximum absorption, and the value is this. So you say, okay, looks like I can get 50%, right? So smallest n. So in vacuum, for sample in vacuum, NS is 1. So then the A max is going to be 50%. So the question is, can we get something bigger than 50%? I said, well, okay, if I can get NS to be what, 0, for example, then I get 100%, right? So the question is this possible? So we just heard this question from our chair, can you engineer your substrates such that you can change the property? And this is something is not crazy for optics people or for radio engineers. We know there's something called anti-reflection coating, right? So you can get no reflection. Everything is absorbed, 100%. So how do we do this? So the idea is that if you have a perfect conductor, perfect mirror, and then you put your sample at quarter wavelength away from your mirror, the effective index for your substrate, mirror plus this vacuum or whatever in between, give you effective index of 0, okay? And then the way to think about this So we know the reflection coefficient, let's say from your substrate is 1 minus ns, 1 plus ns, right? And this is just the Fresnel coefficient. This is right at the surface. Then if you move away, quarter wave, you need to add this propagation factor, and that comes to be I pi, right? So for perfect mirror, this guy is -1, right? That's from Maxwell's equation. And then if you move it to quarter wave, so that means this guy needs multiplied by EI. For quarter wave, this shift is pi, right? And this guy is so that we combine this whole thing, and this is going to be 1, right? -1 be 1. And then, you can get the effective index for the substrate. And that comes to be 0, the effective substrate index. So this way you can get totally screened. This is the anti-reflection coating. Or in radio wave, you block the radar, right? And this actually works only for like a single wavelength. That's the problem. Okay, so I think I have said enough about this simple linear thing. So next, I would like to go back to my list. So polarization, is good to probe symmetry breaking. So I just mentioned a few simple things. So you measure the polarization state upon reflection or transmission, right? So if you see change in polarization, and that could be two potential effects. One is birefringence, so your material is anisotropic. Along one direction, the index is smaller. Along the other direction, index is bigger. So then if you have, linearly polarized light going through, then the two components will propagate at different speed. Once they come back together, the polarization is already changed. So that's one possibility, right? So this is called a birefringence. And another effect is Kerr effect. So let's say your material has different index for left-handed light and right-handed light. So if this is the case, that means the time reversal symmetry is broken. But if it's birefringence, that means the rotation symmetry is broken. So the question is, how do I distinguish, one from the other? So if I want to know whether this is due to time reversal symmetry breaking or it's just the sample has some birefringence, the way easy to check is, for example, you can just rotate your sample. And if it's due to birefringence, then this polarization change is dependent on the angle. And that dependence, usually it's just the cosine 2 theta. Just, because we have one fast axis, one slow axis. So this is cosine 2 theta dependence. And for left and right circular polarized light, no dependence on theta. So this is a quick way to check whether it's rotational symmetry breaking or time reversed symmetry breaking. Okay. So next, let me just quickly mention this nonlinear optics. How much time do I have?
Half an hour.
Half an hour, okay. So I probably should be quicker. I want to talk about something more interesting, yeah? Yeah. If this just tells you whether time reversal symmetry is breaking and probably nothing else. Any time reversal symmetry. So next I want to briefly mention nonlinear optics. And here I want to talk about the specific case of second harmonic generation. Oh, how does this work? That's the end of the blackboard, right?
Run out.
Okay. So probing symmetry properties of 2D materials. By second harmonic generation. And the setup is just very similar to this. So now, now what we do here, we come in with fundamental frequency omega, and in the reflection, we measure the second harmonics, okay? So because it's a second order response, it's 0 when the material or the sample is centrosymmetric, and it's non-zero when only when the sample is non-centrosymmetric. So for honeycomb, if it's graphene, it's centrosymmetric. This is 0. But if it's boron nitride, it breaks center inversion, right? So you have mirror plane, for example, here, or there, you draw it. So we expect to see a nonlinear, second order nonlinear effect. And if you look up the symmetry, this belongs to D3H1. So the ball crystal is stacked such that, one layer is like this. The second layer is 180-degree inverted. I draw it. So this is something called a 2H stacking order. So in this case, it's a different symmetry group. It's 3D3. Okay. So this is not centrosymmetric. This is centrosymmetric. And then 3 layer will be non-centrosymmetric. it goes on and on. So if you do second harmonic, you get a huge signal from one layer, no signal from two layer, large signal from three layer, so on and so forth. And if you do nonlinear optics, you get second harmonic and even higher order harmonics. So let's just focus on second harmonic. And for this symmetry group, there's only one independent non-vanishing second order nonlinear coefficient, and it's XXX, XYY, YYX, and a negative chi to YXY, where X is along the this direction, and this is Y. Okay. So we come in with linearly polarized light. So this is the direction of the electrical field, which makes an angle theta with respect to the x-axis. And we can work out the nonlinear, the second order polarization, which is pi E omega and E omega. So this is a tensor vector and vector, right? And the radiated field at 2 omega is linearly proportional to P2 omega second derivative. If you solve the wave equation, and then the intensity you measure at the second harmonic will be proportional to field module square. And this will be proportional to P2 omega module square, okay? And I don't want to spend too much time on this. I want to talk about something more interesting. So the exercise is clear. You know, you take the non-zero chi2 and put in the right field components, and then you can just carry out. So let me just tell you the result. So the result is that if I look at the projection of the emitted second harmonic along the direction of the fundamental excitation, and this is called I parallel. Second harmonic is parallel to the fundamental. This gives me some intensity and cosine 3 theta square. And if I do the perpendicular projection, I'll get the sine 3 theta square. So this 3 theta should not be too surprising if you just look at the structure. You get 6-fold, and 6-fold is because we are looking at the intensity. So the field is 3-fold degenerate. So if I just draw the pattern on top of it, you get this beautiful flower type pattern. Like this. Experimental results actually are more beautiful than what I put there. Yeah. Yeah.
I think optics has measurement. Is there any restrictions like that?
No, but you can engineer your substrate such that you can enhance the response. You know, there's something you can play with. Yeah. So the typical measurement is just as what I drew over there, and then you can rotate your sample, and this is what you can get. Okay. So now by looking at the direction for maximum second harmonic, you know this is armchair, this is zigzag. So you know the crystallographic orientation. Yeah. Oh yes, yeah.
Which way is that?
So this, then you need to do, instead of intensity, you need to do field measurement. And this can be done by looking at the interference, for example, of your signal with some reference field. Okay, so I have a little bit over 20 minutes left. I want to talk about something more interesting, some newer development. So I mentioned that, you know, one of the difficulties with semiconductor materials is the contact, right? And of course, you know, we are making good progress, you know, making better contacts, this and that. But still, sometimes you cannot have very good contacts. So have alternative approach is interesting and important. So the first kind of a technique I want to discuss is this thing called optically detected resistance or capacitance, okay? And the setup actually is relatively straightforward. And this is work from Feng Wang's group. Okay, so let's say I have a sample here. And I can put two gates. Top gate and the bottom gate. Sorry, I'm making my sample a little bit bigger. So I want to know the transport properties in my sample, you know, in the longitudinal direction. But let's say I cannot make a good contact. So those guys came up with a kind of a clever idea. So they make a sample like this. So this the top gate, and this is the bottom gate, and they flow their sample. So that means, you know, I can put the electrodes here. And then what they do, they add voltage, a DC voltage, and on top of that, they also add a small AC voltage. But the top gate only covers half of the sample. The other half is open for optical measurements. So this is region 1, and this is region 2. And in their sample, the contacts are so bad that in order to inject a charge into the system by changing the gate voltage, you need to wait for a very long time. So let's say something like 1 second gating. So that just means, you know, the contact resistance is very high. The RC constant is, you know, so big. It takes a long time for the charge to flow from the gate to the sample. But then for this AC voltage, you can change it very fast. So the frequency of this AC is much, much bigger than this one hertz, right? So this is 1 hertz. So let's say to be safer, let's make it bigger than 10 hertz, say. So it's 10 times faster, okay. So now if you look at this, you know, on the time scale of this AC voltage, the sample is frozen. You cannot inject a charge, right? But you basically change the effective voltage on the other part. And this actually will induce charge change in the other part. So basically what's happening is that this AC voltage will not change the total charge density in your sample, but will change the charge distribution between left and the right part. So we can describe this setup using an effective circuit. So let me just draw the circuit. So we can have a capacitance, and this will be the capacitance between your sample and the top gate in this part of the sample. And you can also have capacitance between your sample and the bottom gate. And then, your sample has its density of states, right? So this is something we call quantum capacitance. This is just the density of states. And then, if charge flow from here to here, there will be resistance associated with it, right? And then on the other side, we also have capacitor between this guy and that guy. So I have C2, and this whole thing is grounded, right? So this represents the left side, and this represents the right side. Okay, so if you analyze, this circuit, you can solve the effective RC circuit to model the this AC transport property. This delta V AC will induce change on this side. And this change, of course, in the linear case, is going to be proportional to AC modulation you add, and then combination of, the parameters. And those parameters, if you solve this circuit, is something like a C1 divided by C1 plus CB, 1 over C2, C effective plus I omega R. And where this C effective is C1 plus CB Okay. So then this voltage change induced by the AC excitation is going to induce charge on this side, right? So induced AC charge is proportional to this. This is also AC, right? Voltage. With this capacitor. And now the charge change will change the optical property of this piece of sample. And then if you measure the sheet conductivity, this is going to change, right? So this is detected optically. And again, going back to what I said, you measure change in the reflectivity. Refraction contrast change. This is what this guy is measuring, okay, experiment. And so, the quantities we are interested in, one is the CQ, right? The quantum capacitance, it's density of states times E squared, right? And the other one is the resistance. So if you look at this expression, let's forget about this, right? What's important is here. So omega is the AC frequency. So for small omega, this R term is not important, right? You just get some constant, and it mainly reflects, the quantum capacitance. But when you make a omega bigger, this thing should taper down, and then you get the resistance part into your measurement. So if I just look at change as a function of frequency, so initially it's somewhat flat, right? Because when this term is smaller than that, and then it tapers off. Okay, so then you can do the measurement at different frequencies. You get this curve and you fit this, the fit, you will be able to get this quantity and that one. So this is the main idea. So let me just show you some results. And tomorrow I will talk about a different measurement scheme. So this is from that paper, and you see delta R over R, that change in the refractance, right? So refraction contrast as a function of DC voltage. So what this DC voltage does is change the density in your sample. And the sample they studied is this moray made by stacking two different semiconductors. And then on the top, you see filling factor of the moray unit cell. So when you go through some integer or commensurate fractional filling, you see some features showing up, right? So this is just for two different frequencies, but then you do this for many different frequencies, as I said, and do the fit to get this. So the extracted parameters are capacitance and also resistance, right? And let's just look at the resistance. So you see at filling equal to 1/3, 2/3, you have resistant peak. And this they assign to mud insulator and the generalized Wigner crystal. So I don't want to get into the physics. This is something I'm going to talk about tomorrow. But the bottom line is that by making the measurement of the refractance change in this case, you can capture some insulating states in this case. Okay. Much time do I have? 10 minutes. Okay. Yeah. Yeah. Oh yeah. So this is in the heterobilayer. So it has very weak dependence on the displacement field. So that's also the limitation of this technique. Yeah. No. They have yeah. Okay, so I have 10 minutes left. I want to talk about thermodynamics measurement, how to do that. I'll go there. So again, as I said, the difficulty with thermodynamics measurement is the amount of materials so small to work with. And that makes everything so challenging. So what we did, we developed this, sensing technique. So instead of measuring the sample itself, we introduce a sensor. So let me just explain this technique to you. And this technique actually can work with, material that also sensitive to the displacement field. So for typical 2D devices, I already mentioned, you have top gate and you have bottom gate and you have your sample, right? And then if you, hook up with battery and you apply voltage, for example, top gate voltage, bottom gate voltage, and you can also ground your sample and connect to ground here. So those two voltages together can change the doping density and also the displacement field in your sample independently, because you have two knobs and you can change two things. But, you know, as I said, directly measuring the thermodynamic properties of this guy is difficult. So now we're going to introduce a sensor. So I'm going to put a sensor here. And then for this sensor, I can hook up another voltage. So I call it, so I call it a VS. So this is the voltage applied to the sensor, okay? So all those guys are capacitively coupled. So just, you know, and I can do a little bit of electrostatics analysis of, you know, this device. So I can assume a sample has its chemical potential mu, density n, and the sensor also has chemical potential and the density. Okay. So this is just a, you know, parallel plate capacitor in series. If we know the distance between the plate and know the material in the middle, we can compute or even measure the geometrical capacitance for each. So let's call this TDG. That's the distance between the plate, and call this DS. This is the bottom gate. So those are the thickness. And usually in between we put HBN, hexagonal boron nitride. So I can do the field in the capacitor. So this is a E top gate, ES, and then this is the bottom gate. Okay. So, you know, this sensor can be graphene, can be for electrical measurement. It can be monolayer of semiconductor for optical measurements. So let's say you can set your sensor to some reference point. You know, you pick somewhere as your reference point. In the measurements, you know, you can now change those two gates to control the density, also displacement in your sample, right? So once you do that, the sensor chemical potential will be shifted. But you have another gate, this bottom gate, you can always, you know, do some kind of feedback measurement, feedback loop to pull the chemical potential in the sensor to the set point. Right? So this is the function of this bottom gate.
So is the carrier density of the sensor change?
Yeah, but you have the bottom gate to set to some level you like.
Yeah, so after this modification.
No, go back to the point, yeah. And this way, using those parameters, you should be able to get mu and n. So let's just look at, you know, what's going on here. So this is purely electrostatics, right? So we can write down two equations for the from boundary condition. So relate the density in each layer to the fields above and below, right? So we have NE, and this is a epsilon, so to the displacement field, right? ES minus E top gate. And then the density in the sensor is going to be epsilon E back gate minus ES. So this is one set of equation we can write. using boundary condition, and we can write another set of equation by relating electrochemical potential to chemical potential and electrostatic potential. So that's one set. So we can write 3 more equations for the electrochemical potential. So for example, for the top gate, and this will be the chemical potential mu and this field. Mu minus E top gate, D top gate. And similarly, you can write down 3 more equations for EVS and EV bottom gate. So it's mu S. Okay. And now you can solve these equations, so 5 of them, and express this for the chemical potential in your sample. So now mu over E is going to be 1 plus CBG CS VS. So those are the capacitance and related to the distance and epsilon. So, and that's something one can calibrate in situ. You don't need to determine, independently. Minus CBG CS times VG plus 1 plus. Okay, so those 2 terms, dependent on the chemical potential and the doping density in your sensor. And this is something we choose as our set point. So they are constants in the experiment. So, so you can forget about them. Okay. If we're just interested in chemical potential change from one state to another state. So the bottom line now is that chemical potential is determined by this sensor voltage Vs, and also the, I missed backgate. And the backgate voltage you need to apply in order to put the sensor back at the set point. So the question is, what kind of a reference point we can use for monolayer of semiconductor? We already saw has very large response, right? When you have some kind of band-to-band transition. So a very convenient point, the set point will be right at the bottom of one of the bands. Well, conduction band bottom, for example. So then in this case, if we look at reflection or transmission, in this case will be reflection. It's very sensitive to where that chemical potential is. So if I look at this transition. So if the chemical potential is a little bit above this, then this transition can be blocked. And if it's below, you have large transition. So the signal can go something like this. And this is the point, when you block the transition, right? So this is a very sharp edge, and you consider this is like, edge detector. So you can set your, so this is mu s, right? Set your reference point right here. And then every time, when you do something to change the sample property, you use this backgate to bring back the chemical potential of your sensor back to this point to make this and that constant. So this is the measurement scheme. So let me just show you one example. I think I should stop. I have 1 minute left. Let me just show this and I'll quit, okay? Okay, so what we are seeing here is the incompressibility, which is d mu dn. It's the derivative differential change of the chemical potential as function of density. So this x-axis is the doping density in this marine material. And the unit is like how many charge per unit cell. And the y-axis is the displacement field you asked, So you see this very red part, and that means you have a very large incompressibility. And this means you have some kind of insulating states. Right? And again, this is related to density of states. So you see some insulating state at the filling equal to 1, insulating state at a filling 2/3. And if you have sharp eyes, you also see, at 1/3 and then 1/4. So this gives us some kind of insulating state, but that's not the end of the story. We can measure the charge gap size, right? So if you look at the d mu d density at some displacement field, and you see a few line cuts, right? So for example, this is somewhere here. You see a kind of a jump in the incompressibility. So if you integrate this, it's the step change in the chemical potential. And that step change is the gap size, right? So you can read out how big is this gap size. This is on the order of, I don't have the information here, a few millieV. And then this 2/3 is about 1 millieV. And those guys are even weaker. So you can measure, the chemical potential jump due to the insulating states. So I'll probably just stop here. Yeah.
It's particle gap or backlight?
Many particle gap.
Remind me the meaning of the negative.
Oh, okay. So this is very common in 2D electron gas. It's other parts of the energy. So it's due to interaction. In general, when you have a very dilute gas, you have this background of negative incompressibility. This is due to interaction. In any dilute 2D electron gas, you get this.
Is there any system on which both these optical and more compressibility measurements have been done? And I'm just wondering, like, quantitatively, if so, how do they compare quantitatively?
We may have, but I don't know whether it's the traditional compressibility measurement will be just doing capacitance measurement, for those of you who don't know this. And not for this system, but for, other morays we have done. I think they are consistent.
Okay.
Yeah.
Thanks.
How do you interpret the backgrounds of the DVD?
Yeah, so this is something we are still working on it with, so there's different sources, yeah, so that's something a little bit challenging to sort out different sources for the background.
Yeah, so that was very mean and skeptical. But if I was very mean and skeptical, I could say like
Yeah.
changes over some broad ranges of doping are on the same order of DMU-DV that you have for like 1/4. And so then how do I understand like how do I understand?
So, you know, the chemical potential jump, if the state is very clean, let's say you have sample is clean, then it should be like some kind of a step jump, right? And for maybe for this state is a pretty good approximation. So then you have some kind of background, but you know, over a very small doping range, you have a sharp step, and that step measurement is typically reliable. And I have to mention that, you know, all different scanning probe sort of compressibility measurement, even with the SET, you always get this kind of background. So, you know, that's something probably needs more controlled experiment. Oh, yeah. So this is again related to the, you know, background where you set as background. So if the signal is large enough, you will see that step, and you just take that step. You know, when the state is narrow in terms of doping, and in this case, you know, experimentally always some uncertainty, right? So for example, here, you know, we can sort of use this as background, and the area of this peak will be the charge gap size. Yeah. Oh, I forgot to mention that, you know, so in this measurement, mu is a function of density, but then you can imagine, you know, mu can be function of electrical field, magnetic field, or temperature. Then in that case, you can use Maxwell's relation, relate this measurement to polarization, magnetization, entropy, you know, so all those thermodynamic quantities can be extracted if things can be sought out, you know, the sensitivity is good enough. And the advantage here is that, you know, optics can penetrate dual gate, and this is something, you know, SET has a lot of difficulty to measure. And the capacitance, of course, you know, is another measurement, but it's a global measurement. So if you have sample inhomogeneity, all those states will be washed out. You wouldn't be able to see much.